Hello viewers, today in this part of the lecture we will continue to discuss about sequential logic design, and here we will discuss about counters and different types of counter such as 3-bit asynchronous up counter, then the state diagram of an up counter, then we will discuss 3-bit asynchronous down counter, and finally we will discuss 3-bit up down ripple counter. So, what is a counter? Counter is a circuit which counts bits sequentially, and this is done by counting the number of clock pulses arriving at its input. Now, it can count from one number to the next number, and this number does not necessarily start from 0. It can start from any number and it can end at any number. So, here we have shown a counter by considering negative edge JK flip flop, and here we have used 2 JK flip flops to constitute the counter. So, this counter stores memory and can also be used for frequency division. So, what is frequency division? That we will discuss in the subsequent slides. And this is a flip flop with divide by 2 circuit. So, this is also commonly called as divide by 2 circuit. So, here as you can see, the 2 flip flops input is connected to the input of the next flip flop, and the output of the first flip flop is connected to the clock of the next flip flop. Similarly, the other input also is connected to the second flip flop. Now, since it has to be operated in toggle mode, because this is a JK flip flop, so JA, JB, KA, KB should always be equal to 1. Now, here the clock of first flip flop is not same as clock of second flip flop. As I said that the clock of first flip flop is connected to a clock signal, and the clock of second flip flop is connected to the output of first flip flop. Now, let the frequency of clock is Fc. So, for second flip flop the frequency is Fa, and for the next one it is Fb, such that Fa is equal to Fc by 2 and Fb is equal to Fc by 4. So, if we have p number of flip flops where j is equal to 1 and k is equal to 1 for a negative edge flip flop, then the frequency will be divided by f is equal to 2 to the power of p of clock. So, let us see how it is used in this example. So, here it counts from 0 to 3. So, we have to count the clock pulses along with the output QA and QB. So, here we have shown the truth table of the flip flop, and here we have 3 columns, that is clock, QA and QB. So, when clock is the first drop of the clock signal, then the QB is 0 and QA is 0, and when clock is the first or the second drop of the clock signal, then QB is 0, QA is 1. Similarly, for the next 2 drop of the clock signal gives us QB is equal to 1, QA is equal to 0 and QB is equal to 1 and QA is equal to 1. So, this is shown in the timing diagram here in this slide. Here we have shown a clock signal having 8 clock pulses, and the output from the first JK flip flop is represented by QA, and it is, as you can see, it goes from the low level to the high level when the first clock pulse comes down from high to low. And similarly, if we follow the same process, then we will find that the output from the second flip flop is high when the second clock pulse comes down from high to low. So, this can be matched with the frequency of the two flip flops with respect to the frequency of the clock. So, if we count fourth pulse, then it will start repeating. So, it is sufficient to count only 4 pulses of the clock. So, by knowing the output, we can find out the number of pulses passed. So, this is how a counter works. So, if we increase the number of flip flops, then we can increase the counting process, because here we wanted to count from 0 to 3. So, that is why 4 number of clock pulses was sufficient to do the counting process. Now, there exist two type of counters. First is called asynchronous counter or a ripple counter, and the second one is called synchronous counter. For asynchronous counter, the output of preceding flip flop is the clock of next flip flop. So, the flip flops were not clocked simultaneously. As you can see in this slide, we have shown the block diagram for the asynchronous counter. Here we have shown two flip flops A and B, and the clock of first flip flop is connected directly to the clock signal, but the clock of second flip flop is connected to the output of first flip flop. So, these are much slower counters as the clock is distributed in many stages. Here the circuit is simple for more number of stages, because we do not need to think about connecting the clock signal to all the clock inputs of the flip flop. Once we connected the clock signal to the first flip flop, then the corresponding clock signals of the subsequent flip flops will be the output of the preceding flip flop. Now, next discuss about the synchronous counter. In synchronous counter, the clock is connected to all the flip flops simultaneously. Hence, the outputs are not connected to the clock. Unlike the asynchronous counter, here the clock is connected to all the clock inputs of all the flip flops simultaneously. This is a much faster counter as the clock is connected to all the flip flops. Here the circuit becomes little bit complicated as the number of stages increases. So, there is both advantage and disadvantage of the two types of counters that we discussed. So, both synchronous and asynchronous counters are of three types. First one is up counter, which counts upward, that is a smaller number to a larger number, and the next one is down counter, it counts from higher number to a lower number, and finally the third one is a up down counter, which is a combination of both up counter and down counter. Let us discuss each of these asynchronous and synchronous counter little bit in detail. So, the first counter that we will discuss is a 3-bit asynchronous up counter, and the circuit for this particular counter is shown in the slide. Here the output of preceding stage is fed to the clock of next stage, and here the output is represented by 3 bits. For example, it can be 000 or 111 or 100 and so on. And here the output is represented as QA, QB, QC, where QA is the LSB, that is least significant bit, and QC is the MSB, that is most significant bit. So, here as you can see, the 3 flip flops are connected to each other, and the inputs to all the 3 flip flops are 1, and the clock of first flip flop is connected to the clock signal, but the clocks of subsequent flip flops are connected to the output of the preceding flip flop. So, here the clock for flip flop B is connected to the output QA of flip flop A. Similarly, the clock of flip flop C is connected to the output, that is QB of flip flop B, and the outputs are obtained from the output terminals of the 3 flip flops, that is QA, QB and QC. As we discussed that QA is going to be the LSB and QC is going to be the MSB. Now, once we know the circuit, logic circuit, the truth table and timing diagram can be obtained. So, here we have shown the truth table that can be obtained from the logic circuit that we had in the previous slide. So, here the truth table has 5 columns, and that has clock, QC, QB, QA and the corresponding decimal equivalent. So, here because it is a 3-bit state that it counts, so here we will have 8 states, and the 8 states will be having the corresponding decimal equivalent of 0 till 7, and initially the clock, whatever the signal will be, clock signal will be, the outputs from QA, QB and QC will be 0, 0 and 0, and hence the decimal equivalent is 0. But as the first clock signal comes down, the output will be 0, 0 and 1 from QC, QB and QA. So, in this way we can get the output to be equal to 1, 1 and 1 when the 8th clock pulse comes down from high to low, and in this way we can count the corresponding number. Here in this slide we have also shown the timing diagram corresponding to the truth table, and the discussion that we had is validated by using this timing diagram. Similarly, we can also constitute or construct a 4-bit asynchronous up counter. Now, let us find out the state diagram of counter. So, the state diagram of a 2-bit counter will be easy to understand. Once we understand that, we can easily find out the state diagram for 3-bit and higher number of bit counter. For a 2-bit counter, we will need 2 flip flops. So, the maximum count is 3, and the maximum number of states is 4. So, for an up counter it goes from 0 0 to 1 1, and the arrow also follows the same path, that is 0 0 up till 1 1. So, here in this slide we have shown the outputs Q A and Q B for the corresponding input clock pulses. We found that the first state will be 0 0, then the next state will be 0 1, then the next state will be 1 0, and finally it will be 1 1, and the corresponding state table is also shown here, and the arrows follows the path whether it is representing an up counter or a down counter. If it is an up counter, then it goes from 0 0, then to 0 1, then to 1 0, and then to 1 1, and then again comes back to 0 0. Similarly, when it is a down counter, it goes from 1 1 to 1 0 to 0 1 to 0 0, and then comes back to 1 1. Now, let us consider or let us discuss a 3 bit asynchronous down counter. So far we discussed the asynchronous up counter, let us know a little bit about the down counter. So, how to construct a asynchronous down counter? So, there are two ways we can construct the asynchronous down counter. First is by taking out the output from complementary output gates of the flip flop, and the second one is by attaching the clock end of next stage to the complementary output. So, both the ways are represented here by the logic circuit. In the first circuit, on the left hand side bottom, we have the outputs taken out from the complementary outputs of the flip flop, whereas on the right hand side bottom we have the clock signals or the clock input of the subsequent flip flops are connected to the complementary output of the preceding flip flop. So, in both the ways we can construct by following both the ways we can construct the asynchronous down counter. So, if we use whether we use the first method or second method, we will end up with the same counter, same kind of counting, that is a down counter. So, we can show that by considering a 3 bit down counter, and the output is complementary to the output of the up counter. That is how we can validate that this represents, or this logic circuit represents, the 3 bit asynchronous down counter. Here we have shown the truth table for the down counter along with the timing diagram, and if we observe the truth table closely, then we find that the output of the down counter is complementary to the output of the up counter, and hence we can easily say that the down counter is obtained or achieved by using the circuit that was discussed by using the two methods. Here we can also validate the applications or the usefulness of the down counter by following the clock diagram. Now, next we will discuss 3 bit up down ripple counter. So, the counter can count up or down depending upon the instruction that is given, and this instruction is present as an input signal or as a control signal, which is represented here by M. So, M along with a combinational circuit and flip flops make this happen. So, the combinational circuit can be represented by the following block diagram. So, here we have the two inputs Q and Q prime, which are the output of previous flip flop. Then we have another input, that is the control M, and we have output Y, which is connected to the clock of next flip flop. So, we can see that by considering the following example. So, here we have shown three inputs, that is M, Q and Q prime in the truth table, and there is a output column. So, here we have shown 8 states depending on the inputs that are given at M, Q and Q prime. So, how to decide the output here? So, we can assign a logic to get the output, that is when M is equal to 0, Y will do the up counting, and when M is equal to 1, Y will do the down counting. So, when the up counting is happening, the clock of the subsequent flip flops are coming from the Q output of the preceding flip flop. Similarly, when the down counting is happening, the clock of the subsequent flip flops are coming from the complementary output of the preceding flip flop. So, once we know that, now once we get the output, we can write the Y column or the output column easily. So, once we get the truth table, we can now simplify the circuit by following the K map, and here we have a K map of 8 tables or 8 boxes, and they are Q bar Q prime bar, Q bar Q prime, Q Q prime and Q Q prime bar in the vertical direction, and M bar and M in the horizontal direction. So, if we simplify this Q map, then we will find the expression for the output is equal to Y is equal to Q prime M plus Q M bar, and this can be represented by the following combinational circuit shown in this slide. So, this combinational circuit along with the M control and the 3 flip flops can be used to construct a 3-bit up down ripple counter. So, this is how we can construct a up counter or a down counter or a up down ripple counter. So, viewer, today we discussed a very important concept, and that is the concepts of counter, and we can easily summarize the concepts of counter by the following few important points. So, first we started the discussion of counter, what is the role of counter in a logic circuit, and then we discussed about two types of counter, that is asynchronous counter and synchronous counter. What is the difference between the two types of counter? Then we discussed that each of these counter is again subdivided into 3 categories, that is up counter, down counter or up down counter, and we discussed 3-bit asynchronous up counter, 3-bit asynchronous down counter and 3-bit up down ripple counter. So, viewers, I hope you would have liked today's session. Thank you very much.